Hello everyone, and welcome. Today, I'm presenting Neighbor GRPO, our work accepted at CVPR 2026. We introduce a fundamentally new approach to aligning flow, matching generative models with human preferences through what we call contrastive ODE optimization. This is joint work by authors from the Chinese University of Hong Kong, CUEC, and Vivix Group Limited. Over the next 5 minutes, I'll walk you through 5 parts of this work: the background and motivation, our core theoretical insight, the Neighbor GRPO method, key implementation strategies, and the experimental results. Let's begin with the background. Flow matching models, such as the widely used flux model, generate images by learning deterministic ordinary differential equation trajectories from Gaussian noise to clean data. This deterministic property gives flow matching significant advantages with sampling efficiency and generation quality. However, it also creates a fundamental conflict. Reinforcement learning fundamentally depends on stochastic exploration to discover better policies, while ODE sampling is entirely deterministic. Existing approaches like Flow GRPO and Dance GRPO address this by converting the ODE into an equivalent SDE, introducing noise at every step. But this creates 3 critical problems. First, inefficient credit assignment. Each sample independent forward-backward passes, so computational cost scales linearly with group size. Second, incompatibility with high-order solvers. SDE sampling is restricted to first-order methods, preventing the use of efficient solvers like DPM. Third, flattening. When group rewards become similar, the advantage function becomes nearly uniform, leading to weak updates and eventually reward hacking artifacts. Our key insight re-examines SDE-based GRPO from a distance optimization perspective. Under the isotropic Gaussian policy, the policy gradient objective actually reduces to simple distance-based updates. High-reward candidates pull the anchor closer, while low-reward ones. This means SDE-based GRPO has been secretly performing contrastive learning all along. And this naturally leads to our central question. If the goal is just contrastive optimization, why do we need the expensive SDE conversion at all? Can we perform effective GRPO directly on deterministic ODE trajectories? Neighbor GRPO answers this in 3 elegant steps. First, instead of using SDE noise injection, we generate candidate trajectories by simply perturbing the initial noise conditions of the ODE solver, creating a natural neighborhood. Second, we define a softmax distance-based surrogate leaping policy over all candidates. This policy provides the necessary policy ratios and gradients without any SDE conversion whatsoever. Third, and most importantly, our method fully preserves all advantages of deterministic ODE sampling: high-order solver compatibility, efficient credit assignment, and completely noise-free inference. 3 strategies make Neighbor GRPO practical. First is symmetric anchor sampling. By the Johnson-Linden-Strauss lemma, initial noises in a group are almost equidistant, so any candidate can serve as anchor. This reduces backward passes from order G to order B per iteration, achieving up to 12x speedup. Second is groupwise quasi-norm reweighting. We replace the standard L2 normalization with an LP norm, where P is less than 2. This sparsity-inducing norm downweights flat advantage signals, preventing reward flattening. Figures, reducing P from 2 to 0.8, visibly improves generation quality. Third, we directly leverage high-order solvers, like DPM+, for data collection, enabling efficient training with as few as 8 steps. For experiments, we use Flux, 1dev, and train on the HPDV2 dataset containing over 100,000 prompts. We evaluate across 6 metrics, covering both in-domain preference and out-of-domain generalization. Our baselines include dance mixed GRPO, and branch GRPO. The results are compelling. Neighbor GRPO converges fastest, reaching HPS above 0.35 in just 50 iterations, while all baselines require over 200 iterations. It leads on all out-of-domain metrics, with user study win rates of against mixed GRPO and 61% against dance GRPO. Training efficiency is dramatically improved. NFE theta drops from 14 to just 1.33. And per iteration time falls from 238 seconds to only 45 seconds. To summarize, Neighbor GRPO fundamentally rethinks GRPO for flow models by revealing its contrastive learning nature. It enables effective policy optimization without SDE conversion, achieves up to 12x training speedup, and delivers superior. Thank you very much for your attention.